So these are called first order linear differential equations. I mentioned this yesterday. First order means we're talking about first derivative instead of like a second or third or whatever derivative. And then linear means that essentially means that you'll see here in a second, the p of x is linear, like a key factor in this is linear as opposed to being like quadratic or whatever. And if you do end up taking differential equations, you'll find out that like little tiny tweaks to the diff-EQ, like seemingly innocent little changes, like for instance going from x to the first x squared, radically change the nature of the question. Or instead of like x, it's like e to the x, or instead of e to the x, it's, I don't know, square root of x, or who knows, whatever. Little tiny tweaks make it a far more simple or a far more complicated question, even though it seems like it wouldn't be that big of a deal. A lot of times it is. And so here is what we do. The first thing we got to do is we need to recognize what we have, and we need to try to write it in what we call standard form. And standard form is you've got the derivative plus some function times y, and that some function needs to be linear. That's why it's called first order linear. So p of x needs to be linear. So it'd be some function in terms of x, or perhaps just a constant, times y equals some other function in terms of x. Right? So this would be standard form. And when we look at our first example like we did yesterday, you'd see pretty quickly that you can't separate the variables. We can't do our standard, we'll divide by this, multiply by that, and all of a sudden the x's and the y's are spread apart, separated, and we're good. And so that strategy simply won't work in this form. And so once we've identified the p and the q, the most key step, or one of the most key steps, is this right here. We need to develop what's called the integrating factor. This is going to be an expression that we multiply everything by to turn it into something that we can separate and that actually makes it, relatively straightforward to do from there. So the integrating factor is specifically e to the integral of p of x. E to the integral of p of x. P of x being the function right here, the one that's being multiplied times y in our standard form. So, p of x is going to be whatever it's going to be, and so we do our integral of that, and we come up with this integrating factor e to the whatever it ends up being. Okay, so once we've done that, what we're going to do is we are going to multiply every single term by that integrating factor. So we're just going to distribute that throughout all three of the terms that we had at the beginning, and so that would give us something like this, right? You see that here, first term got multiplied by our integrating factor, second term, third term, they all got multiplied by that integrating factor, which is a very strategic expression that will allow this to work. Okay, so once you've done that, as I mentioned up here, you're going to have two choices. I know what I like to do. I know what pops out at me. You'll have to decide what pops out to you. You can either use a formula, or you can just recognize the left side. I'm going to show you, if you want to memorize the formula, be my guest. I got no problem with that. It takes very little effort once you've memorized the formula. I am very interested in you understanding a little bit about why the formula is what it is. And so I'm going to show you the alternative method. The alternative is to recognize the left side really is a product rule, break that product rule back apart, do a couple of steps, and get to an answer. That make sense? I'll show you those steps in a second. But if you want to memorize that formula, that's really what it is. It's just y equals all that junk over there. It's very cold and heartless and somewhat meaningless as a formula, right? It's just like, oh, magic, look, woo, right? I'll show you where it comes from and how we could apply it here on a couple of these and see what you think. So, I say enough chit-chat. We should try one. Anybody have any?
Let's do it.
Yeah, let's do this. I agree. Okay. You're putting your big boy and big girl shoes on now, so. Okay, so example, there we go, zoom a little bit. Okay, example number one, keyword. I realize this is a new topic, but there is a very key term in there, right? General solution. What is the trademark of a general solution? It's going to have a plus C in there somewhere, right? C is going to be incorporated into this. We won't be able to find the C. As you notice, there is no initial condition given, so even if we really wanted to find the particular solution, we can't because we don't know what the initial condition would have to be. So I've set this one up, or allowed this one to be set up really nicely for us. Notice how this does perfectly fit that standard setup for a first order linear differential equation. It's dy dx plus 2xy equals 10x And so that perfectly, I'll erase this in a second, that perfectly, well, maybe I won't, perfectly goes with this. So you can see dy dx is exactly where it's supposed to be. 2x is in the place of p of x. And then q of x, based on the way this is written, would have to be 10x, right? So we're just matching up the different pieces with where they are. Still good? Any questions? Okay.
Wait, so are P and Q just any type of constant?
So P and Q could be a constant. Yes, they could be, but they could also be differentiable functions in terms of x.
Okay.
So, so I would say 2x is in the same place as P of x. So here in a second, we're going to say, all right, we think P of x would have to be 2x. And then 10x is in the same place as Q of x. So I'd say those two would have to go together. Okay. All right. Any other questions? Okay. So I'm going to come over here to the side, and I'm going to try to process this over here. In order for me to process this, I have to find what's called that integrating factor, the thing that's going to make all this go a little, well, going to make it go at all. And the integrating factor, usually the letter u is used for that, although it doesn't really matter all that much. U of x equals e to the integral of p of x dx. And if you want to know why that is, someday you'll have to take what's called a real analysis class. That all these awesome things we use in calculus, some of which I explained to you, others of which, like this one, I won't. Real analysis is basically, I guess the class could be called Prove It. It's basically proofs for all this stuff. So I don't know if you're interested someday, feel free. So here we go. I'm going to say then u of x equals e to the integral of 2x dx. And thankfully that's a pretty straightforward integral for us to do, right? So this would equal e to the x squared. Okay? Any questions so far? Okay. So once we found that integrating factor, what we're going to do is we're going to multiply everything in our differential equation by that. Question?
Am I overthinking it, or is it supposed to be e to the x squared plus c?
Yeah, you want to put a plus c in there, don't you?
Yeah.
Yeah, I know you want to put a plus c in there. What we're going to think about this is we have not, like the overall idea is to solve the differential equation. And so as we solve that, we're going to have our plus c,
Okay.
right? We think of this as like kind of an in-between step. Let's see
I didn't know
here.
if I was like overthinking it or.
No, I think it's a valid question. I think it's a valid question. I'll think about if I want to say anything more about that. But for now, Darian, maybe just suspend a little bit that thought. Okay. So we're going to multiply everything through by that. That makes sense? Okay. So it's going to be, I'll do this. No, I'll do it in a different color, I guess. So dy dx, and then I'm going to multiply by e to the x squared. Plus oh, I keep picking the wrong color. I got to have the same color. There we go. Plus, there we go. I've got 2xy e to the x squared. Thanks, Austin.
Sure.
How'd it go?
What?
Did it go okay?
Yeah.
All right. Okay, so I've distributed that integrating factor. I wrote it in different colors just because this thing, it's pretty easy for it to look all jumbled up, right? There's a lot of stuff going on. You can all see it? Okay. So the right side is pretty set. And so what I'm going to do with that right side is just go back and say, okay, it's 10x times e to the x squared. And here's where you'd have that decision, right? Once you found your integrating factor, you could just use that formula and say, hey, a formula, fantastic. Or you could recognize something. This is what I want to do here with you guys. The left side is a sum, isn't it? Right, you got something or other plus something else. And so whenever somebody does the product rule, isn't that the result? 1d2 plus 2d1. So not everything that's in addition is the result of a product rule, but that's at least a commonality, right? all product rules should result in something plus something. So we've got that. We've got that right there. But the question is, does this perfectly fit the product rule? And if we've done everything right, it should. So here's what I'm going to do. I'm going to take that whole left side and I'm going to rewrite it as a product rule. And we're going to make an, I'm not going to say guess, but we're going to make an educated supposition on here. And we're going to say we think this is it, and we can check it. Okay? So I'm going to say that the left side is this. It is ddx of a product. ddx of a product. And we need to figure out what those two things that we're doing the derivative of a product would have to be in order for it to work with the pattern above. So will you guys take a minute and like reverse engineer this a little bit? Does that make sense? Please don't blurt. Just think for if you think you've got it. Take a second and kind of reverse engineer this and then maybe check it. See if you can figure out what the two factors would have to be in order for the product rule to work with this. Okay, so take a minute and do that. I'll let you do that on your own. Or work together. E to the x squared times y. Like that? Okay, so let's mentally check this, or you know what, I'll just do it on paper here, or on the screen. So if we're doing ddx of that, we'd get 1 d2, so ddx of y is dy dx, because of the chain rule, plus 2, and then ddx of e to the x squared, it's another chain rule, right? So it'd be times e to the x squared times the chain rule factor of 2x. So we should be able to compare this with this and have the same thing, and we do. So if we've done this right, this is exactly the type of pattern that should show up. And this is me just trying to get around using that formula, just because that seems, while efficient, it seems a little disingenuous, right? Just kind of magic. Let me get rid of all this stuff. Are you guys satisfied that that works, that that really is a product rule? Okay. So we're gonna separate some things out here a little bit. What I'm going to do is I'm going to multiply both sides by dx. So if I multiply both sides by dx, I'm going to get the differential of e to the x squared times y is equal to 10x e to the x squared times dx. So this is kind of a weird notation, right? It's like d of e to the x squared times y. But this is really what the antiderivative undoes. It undoes differentials. And so when you think about this left side over here, think of this left side as being sort of like this. It's d, it's a differential of this, a differential of that. It's just the differential of the thing on the left is a bit more complicated than one on the right. It doesn't make too much of a difference. The antiderivative is still going to undo the differential of part of the expression. Oops. So once we've done this, we can find the antiderivative. So I would antidifferentiate, and I think I'd exclude that 10 out of there, just to make it a little bit simpler, perhaps. So this gives me e to the x squared times y equals, what do you guys think about that right side?
1/2.
1/2 of 10, right?
Yeah.
So 5. 5e to the x squared plus c. Now you can do u substitution over there. You can do, Timmy messed up the chain rule, but it is a pretty straightforward substitution or adjustment. It did ask for the general solution, so my final step would be to get the y all by itself. So to get the y all by itself, I need to divide by e to the x squared. So my general solution would be y equals 5 plus c over e to the x squared. And no, c over e to the x squared is not some other c, right? Because e to the x squared is definitely not a constant. If we did have an initial condition, we could use it at some point in there after the antiderivatives and find the c, but we didn't have that. We got this general solution, so we'd stop right there. In fact, some books will actually say, depending on the book, the AP would not agree with this, but some books would actually say that this right here is a general solution, and okay with that, it's just not solved for y. But either one of those, with the AP being, you've got to always solve for y when you get the solution to a differential equation. Alyssa, you have a little concerned look on your face.
What exactly is D? Like on the left side?
What is d?
Yeah. Like,
Oh.
How does like dx? Like I get the dx thing. I don't.
So yeah, I'm going to erase some stuff and kind of show where that formula would come into play. Listen, the formula is going to feel a little shorter. I just kind of want to show you like a process to actually get there instead of the magic formula. So I'm going to erase all this stuff. In fact, I'm going to erase all of this stuff. So this would be the point where you'd want to use your formula. Once you have found your integrating factor of e to the x squared, there we go. So if you got the formula memorized, which I realize memorizing formulas is not that hard, it's also somewhat meaningless unless you know where they came from a little bit. So you use the formula right here. So you would say y equals 1 over u to the u of x times the integral of q of x times u of x dx. So then what you do, you could maybe get the 10 out of there. And you still got to do that integral, of course. So you'd say that we're missing a factor of 2. So I'll put that 2 in there. So we need to also divide by 2 on the outside if we're going to be doing that. So this would give me 5 over e to the x squared. The reverse chain rule is perfectly set up there on the inside. And so we would just say that that ends up being e to the x squared plus c. And then to finish this out, you would just distribute. So if you distribute, you end up with 5 plus 5c over e to the x squared equals y. And of course, 5c could be simplified to be a different c, right? Giving us, I realize I erased the answer already, but giving us the same answer as what we had before. So yeah, you could use the formula, totally. Makes it a little bit easier. But again, I wanted you to see like where that product rule came from and why the formula ends up kind of working out the way that it does. Is that helpful?
Yes.
Okay. You're welcome. Any other questions? Melissa, I see the frowny face.
Why is there a 5? Why is it 5 plus 5c on the side, but it's just 5
Plus c.
on the other side?
So what we'd have to say here, of course, 5 is a constant multiple, c is a constant, so 5 times c would just be a different c.
Okay.
And so if we were doing a particular solution, then the timing in which we applied that initial condition to find the particular solution would make all the difference, right? So 5c is still just some other c, and that's why we just had a c on the other one. But like I said, timing would be everything on when did I apply the initial condition, what does it mean? Because then the 5 would either need to be in there or not, but in the end we should get the same
Okay.
particular solution if we did have that initial condition. Okay. Okay, I'm seeing no more frowny faces. Okay, awesome. So let's take a look at our other one here, example number 2. Let's see here. Let's do that. You got it in front of you, right? I kind of zoomed out a little bit so I could write, have a little more room. So I'm going to get you started on this one, and I'm going to let you guys run with it for a while, and we'll close it up. And I really do honestly hate to say this. I don't know if we're going to have time for the application. We're taking our time here and going slow. The application, while good, is going to take more than probably the 3 minutes we'll have at the end. So let's not try to rush through this. Let's make sure we're good at what we're doing. There is no application on your test. I'll just tell you that right now. If you are curious, I would never do that to you. If you are curious, it is a fascinating situation. That's how the application is. Basically, you've got a solution of, I don't remember what it is, bromine, however you say that. You've got a solution of a certain amount of bromine, and you've got a solution being pumped into a tank, which should sound familiar. And you also have a certain solution being drained out of the tank. The tank is being mixed up the whole time, and it wants to know at what time you'll have a certain amount of bromine in the tank. So it's like a fairly simplistic looking situation, but a fairly complicated thing that you got to do. So if you're interested in that someday, just drop by and be happy to.
So is this on the CalPC test?
Say again?
Is this concept on the CalPC test?
No, it is definitely not.
Okay.
All of 6.4. This is just the bonus.
Okay.
So You should not be running into this on the BC test at all. If you're like, hey, it's a linear or first order linear differential, you'd be like, no, do something else. Okay, so I want to help you guys get started with this one, and then I'll let you run with it a little bit. Notice how this, as it stands, is not perfectly written in that standard form. Remember, standard form is dy dx all by itself plus p of x times y is equal to q of x. It's got to be that exact standard form, and this is not in that. What do I need to do to get it to that point? Divide by 2x. That's right. So if I divide by 2x, that'll get me there, and I'll show that, and then we'll kind of resolve that, and I'll let you guys kind of go with it from there. So let's agree where we're going to start with this. If you do that, you're going to get dy dx is left over minus, maybe we should write it as 1 over 2x times y equals, you want to write it as like 1/2 x squared over 2? Sure. So x squared over 2 minus 1/2. Is that acceptable? So let's all start there. And that is in standard form now after that little division by 2x and the converting the y prime over to dy dx. So if you guys would, take that, see if you can run with it. There's some little tricky things waiting for you. And I will say this, if you happen to run into any like e's or ln's anywhere, think about simplifying those.
No.
Think about some.
Consider.
Okay.
Consider. That should make your life easier if you can simplify things. But yeah, take a few minutes, try it. This is my p of x. So we're going to say u of x equals e to the integral of that. So then I would say that equals e to the negative 1/2 integral of 1 over x dx. I think this is a really useful thing to do to get that constant multiple out of there. It's going to make it easier at the end. And so I'd say finally, u of x equals e to the negative 1/2 natural log of x. Does that make sense? You can go with that, but I think it's easier to keep trying to simplify it. We can simplify logs a lot of times. So I'm going to keep going and say this is really e to the natural log of x to the negative 1/2. And it's at this point really the big simplification happens, right? Because e to the ln of something just becomes that something. So this would equal x to the negative 1/2. I think it's best to do it this way because when you're multiplying the whole equation through by stuff, I'd rather multiply through by that as opposed to e to the ln of blah, blah, blah. I mean, it's just more complicated, more things to get lost. So I would do that. So I think working with that integrating factor, getting that integrating factor to be as easy to use as possible, I think is a smart thing to do. Okay, so I'm going to write this now with that integrating factor in there. So it's going to be x to the negative 1/2 times dy dx minus 1 over 2x times x to the negative 1/2 times y equals, maybe I'll just write it as x squared over 2 minus 1/2 times x to the negative 1/2. Is that okay?
Yeah.
The right side is just a distributive property, so I'd say the right side is x to the 3/2 divided by 2 minus x to the negative 1/2 divided by 2. And I am not going to use the formula here. We can all plug and chug if we want, but I'm going to find the product rule. Product rule is going to be ddx of something. I just got to figure out what the two factors are. I would say, as an educated guess, that my two factors are going to be y times x to the negative 1/2. And I think we can confirm that pretty easily by using the product rule to redo ddx of that. But you're often going to find, it depends on how you write it, but you're going to find that one of your factors is almost always going to be the y. Right? Should pretty much always work out that way. And then the other one is going to be attached to this other term. The other factor will be attached to that other term. But if in doubt, just make an educated guess. Try to do the product rule. See if it works out. Okay, so we would then separate out the differentials here. So you'd get d of this is that weird step, equals all of this stuff dx. And then we do our antiderivative. So antiderivative. This will give me yx to the negative 1/2 equals, let's see here, the 5/2. So I'm getting x to the 5/2 over 5. Is that right? So here, I'll do it on the board really quick.
Thank you.
Thank you.
I did plus the after flipping like x to the negative 1/2 over, and then did plus c, so I got the wrong answer.
Thank you.
Well, you too, Caleb. Thank you. It should still work out though.
Oh, really?
Yeah, it really should. So like if you, okay, so let's look at it. If you